This is the MAT 125, video number 3, analyzing arguments with truth tables. Use a truth table to analyze the validity of an argument when the statements involve connectives such as if then, or, and, not, and if and only if. The form of an argument in general is like this. You have a premise 1, a premise number 2, and perhaps there could be premise 3 and 4 and so on. And then from those premises, some conclusion is given. So in analyzing all of the arguments with truth tables, what you do is you take every premise and link them all together with an and, with a conjunction. Link them all together and group them, and then use that as a single antecedent. Use the arrow or the implies to whatever the statement was that was the given conclusion. So this is the general form for any argument with any number of premises. Every premise would just be linked together with another and. All of those premises are linked together, then there's an implies the conclusion in this general form. And so let's take a look at an example. First example says, if you take the medicine, then you will feel better. You feel better, and therefore you took the medicine. So that is the argument, and the first two lines are premises. The last line, because it says therefore, that's the conclusion. Let's write it in a symbolic form. So what I have here is a form that's P implies Q as the first premise. That is, you take the medicine. That was P. You feel better. That's the statement Q. And so the second premise is you feel better. So we'll say Q, and then draw a line to separate the first premise and the second premise. The conclusion is you took the medicine. So if you take the medicine, then you feel better. You do feel better, and therefore you did take the medicine. Is this a valid or invalid argument? So the way to look at this is, if we accept each of these premises as true, would the conclusion logically have to be true? So generally what you could do is take each premise and link them together with ands. So the first premise, this is premise 1. Second premise is Q. So we'll say and Q. This is premise 2. And here's the conclusion. So some people put 3 dots to indicate the conclusion. Some people, I think our book actually has just 1 dot to indicate the conclusion. And it doesn't really matter if you put 3 dots or 1 dot. For me, I think what's sufficient is if you just draw the line, then it's clear enough that under the line is the conclusion. So what is important though is that I group the premises together, use an arrow for the conditional, and then write the conclusion. In this case, the conclusion is P. Now what we'll need to do is a truth table for this entire statement to see if it's true in every case. Because it's a conditional, what I'm basically doing, there's one situation where a conditional would be false, and that is if the premises are all true and the conclusion is false. So under all the conditions of P and Q, is there any way that all of this could be true while the while the statement P, while the conclusion is false? And we'll discover that by listing out all the cases in the truth table. So let's do that. So there are only 2 variables here. So we'll use P and Q, and we'll get every single case where we've got truth values for P and Q. So we've got the possibility they are both true. You can go 1 true and 1 false, false, true, or they could be both false. Now, in order to do a truth table for this entire statement, I'll start with the conditional P implies Q. That's true in every case except for this one case here, where you go from true to false in exactly only that direction. If it goes from true to false, then it's false. Otherwise, that conditional is a true statement. The next column, I could do everything the and of the two premises. And so that's just an and of columns. This is column 1. Here's column 2. This is column 3. I'm trying to do an and of column 2 and 3. And with these two columns, well, these are both true, so the and is true. This will be false. Here, these are both true. This is true. And in order for the and to be true, they have to be both components have to be true. They're not both true. This one is false. We've already got a column for P, of course. So now we can finish this table by doing the entire statement, a truth value for the entire statement. So if this is column 4, then what I'm looking at is column 4 implies column 1. I'm doing the rule for the conditional from columns 4 to column 1. So the conditional, the rule was true in every case except you go true to false. So this is true to true. That one's true. This is false to true. So it's true. Now here from 4 to 1, I go from true to false. So I know this is false. And then these are both false. So the conditional is true. Well, from that last column, I know that that statement is not always true. So we did uncover a situation where the conditional that is the entire argument as a single statement, it is not actually true. It's possible that P implies Q is true and Q is true, but P is actually false. So that's exactly where that occurred. So we know that since it's the argument as a single statement is not always true, we could say the argument is invalid. So that is really the conclusion. The question was whether or not the argument is valid or not. The answer is invalid. Let's take a look at another example. Example 2 says, if you wear a tinfoil hat, then aliens cannot read your mind. Second premise, you wear a tinfoil hat. Conclusion, therefore, aliens cannot read your mind. The question is that a valid or invalid argument? What I mean is, if the premises were true, would the conclusion logically follow? It's like, it doesn't really matter whether or not the first premise is actually really true. The question is just, like you might say, for the sake of argument, if it were true, if the first premise were true, and the second premise were actually true, if both of the premises were actually true, and therefore the and of the both of them would be true, would that logically imply the conclusion as a conditional is the whole statement always true, regardless of whether the P and Q values are actually true in and of themselves. I'm not assuming that P is true or Q is true. All I'm doing is I'm assuming the first premise is true. And I'm assuming the second premise is true. And I'm checking to see if that's sufficient to conclude, to determine that the conclusion would have to be true. So we have another argument we can put in symbolic form. This is P implies Q. Second premise is P. Conclusion would be Q. You wear tinfoil hat. That's P. Aliens cannot read your mind. I'm going to call that Q. You could just as well have called it not Q, but it's simple enough to say Q is aliens cannot read your mind. That's true or false. Here's the statement P, you wear a tinfoil hat. Conclusion, aliens cannot read your mind. That's Q. Is it a valid or invalid argument? Study it just as before. Take the first premise, link it to the second premise with an and. Actually, I don't really need the parenthesis there. So we have those two premises that imply this conclusion. So we'll do a truth table once again for this entire statement. And with this one just as well, we have two variables, P and Q. So we're looking at the general structure of the argument, whether it's logically valid. That is, if this statement, this conditional, which is in fact actually the given argument, whether that is actually always true, regardless of whether P and Q themselves are individually true. It's basically we're saying if both of these were true, that would have to be true. Okay, so let's go through it. So we got both P and Q could be true, true, false. We have the possibility of false and true. And we have this fourth case, both P and Q are false. So it looks like this one also has the conditional P implies Q. So in this case, it's true. In this case, the conditional is false. In this case, it's true. And there it's true. The next column I'll do is the whole entire conjunction of the two premises. So that's P implies Q and P. So it is columns 1 and 3. Columns 1 and 3. Here's 1. Here's 3. And I'm doing an and with those. So and is true only when both parts are true. It's true here. False in this case. False in this case. False in that case. And now we can do the entire argument. P implies Q. And P all implies Q. So we need to look at column 4 implies column 2. So I need to use the rule for the conditional here from columns 4 back to column 2. So true to true, it's true. False to false, this is true. False to true, in that order, it's true. And false to false, it's true. So this argument is always true, and therefore it's valid. So we would say the argument is valid, and what we mean is that logically the structure itself, the underlying logic of the argument, is actually a valid form of argument. Of course, it's completely nutty because the first premise wasn't really true. Let's look at it again. It said, if you wear a tinfoil hat, then aliens cannot read your mind. Second premise, you wear a tinfoil hat. Conclusion, aliens cannot read your mind. What we're saying here is that if the first premise was true and the second premise was true, the conclusion would have to be true. And so therefore the structure is a valid structure, a valid form of reasoning, even if it's based on premises that are crazy or, maybe true, maybe not. We can logically conclude deductively that the form of argument itself, the underlying logic of the argument, is actually a valid form of reasoning. Okay, so now really you don't actually have to go through a truth table for many of the arguments that you will see. They will fall into one of 4 very common and important valid forms, or you may discover the argument that you are presented with is one of 4 common and important invalid forms. In other words, the real math behind this is to completely abstract. It doesn't really matter what the words are. It's the structure of the argument itself that we're actually after in the abstract sense. And so you can recognize that any argument that has this form would be valid. And that's the one that we just did. Right? P implies Q, and P conclusion is Q. We just did that. I'm saying this is a valid form, and one of the names for that form, because it's such a common and important form, it's called direct reasoning. It has a very old Latin name because this is a very ancient form that goes all the way back to Aristotle in the very beginning of understanding logic in this sort of classical sense. So the Latin name is modus ponens. Modus ponens translate to something like method, direct method. Modus is method, ponens is like direct. So this is a direct method of reasoning. And so we've just looked at this one. This is another one. It hasn't come up yet in our examples, but this one is modus tollens. I think the Latin is something like reverse, or sort of a reverse method. Um, I don't know a Latin name for this one, but this is a very common uh, valid form that we will see an example of in a minute, called transitive reasoning. And here is a form that involves the disjunction, and it's a valid form, and so I've just given it the name valid disjunctive reasoning. So all of these are sort of classic valid methods of reasoning that are always true because they will always come out always true in that final column in the truth table. And what I'm trying to say here is that you wouldn't have to do a truth table every single time if you were encountered one of these arguments. The mathematical idea is that you could recognize the form and say, well, that form is a valid form, and then from that would be sufficient to make a conclusion, unless the question said specifically to do a truth table. And while we're on the topic, these are all invalid forms. I think the first one that we saw was this one. The first example I did was uh, fallacy of the converse. Let's go back and look at example one again. This form right here is an invalid form. This is the fallacy of the converse. It's because the converse is not logically equivalent to a given conditional. And if you began with the first premise as a conditional, to then assume that Q is true and conclude that P would therefore be true as well is sort of assuming that the converse is equivalent to the given conditional, and it isn't, and this is an invalid form. So fallacy just means an invalid argument. So that's what you saw in example one, was a form that was the fallacy of the converse and therefore invalid. Anytime you encounter any argument that has that particular form, you wouldn't necessarily have to do a truth table. You could just recognize that it's an invalid form, and specifically it's the fallacy of the converse. If the question was, what form is it? What's the name of the form? The answer is it's fallacy of the converse. And unless the question specifically said, do the truth table, you wouldn't necessarily have to do the truth table. You could, if you recognize the form, right? So let's go back to our list there. Yeah, so this is the one, example one, that we saw, so that anytime you encounter any other arguments with that same form, you could immediately conclude that it's an invalid argument just by the structure of the argument. Similarly with these others, any argument that had this form, you say that's an invalid argument. And if the question asks specifically for the name of that form is the fallacy of the inverse. It's an invalid form of reasoning that's called the fallacy of the inverse. And here's a form that is similar to transitive, but it's not a valid form. P implies Q, and then Q implies R, but then to make the conclusion that R implies P is sort of like mixing the converse and the transitive reasoning together, and so it's another invalid argument. And this is a argument that uses the disjunction, so it has an or in it, but it's an invalid form in general, and so I've just come up with a name I call it invalid disjunctive reasoning. It's very similar to the valid disjunctive reasoning, but just slightly different. You look very carefully, you'll see the difference, and one is valid, the other one is valid, this one's invalid. There are all kinds of little variations that could occur. And so you might, with some practice, begin to recognize the essence of the argument or the essence of the form, recognizing when it's the valid versus the invalid form. If you don't recognize that, or as you get, practice this, you may decide to do the truth table just to be sure. But if you saw something that had this form, or let's say it was equivalent to this form, then you can conclude invalid. Let's try another example. Okay, example 3 says, if you take the medicine, then you will feel better. If premise 2 says, you didn't take the medicine, the conclusion, therefore, you will not feel better. So let's look at the form. If you take the medicine, then you feel better. Premise 2, you didn't take the medicine. That could be negation of P. Conclusion, you will not feel better, not Q. Well, I don't have to go through the truth table because I recognize this form. This is the fallacy of the inverse. So that's the answer. It's an invalid argument. take a look at example 4. On Saturday, I will sleep late or go to the gym. I slept late, therefore I didn't go to the gym. So we'll look at uh, really the logical form here is P or Q. We don't really have any reason to include the um, condition that it was on Saturday. We'll just say I will sleep late, that's P, or go to the gym, that's Q. Premise 2, I slept late. Conclusion, I didn't go to the gym, negation of Q. All right, well, that form is one of the 4 that is an invalid form. Because I recognize the form, for that reason, I don't actually have to go through the truth table. I can say that it's invalid. There's another way to recognize that it's invalid, though. You could say that understanding the or logically, it would be true if either P or Q was true, or if they're both true. And so you could sort of see how intuitively, if we said P or Q happens, and then we say P happens, to say that Q didn't happen would be logically an error because they could both happen, right? We could sleep late and still go to the gym. So the answer is invalid. All right, let's take a look here at example number 5. We've got if the horse is lost, then the battle is lost. If the battle is lost, then the kingdom is lost. Therefore, if the horse is lost, the kingdom is lost. So if we break this up into its abstract form, we could take this statement here as P, the horse is lost, the battle is lost, that's Q. Here's Q again. So then the kingdom is lost. So let's call this R because that is a different statement. So we have, therefore, if the horse is lost, P, the kingdom is lost. You don't really have to say the word then. It's sort of understood following the word if. The horse is lost, then the kingdom is lost. So this is R again. Oops, here. This is R. All right, so the form is P implies Q. Q implies R. Conclusion is P implies R. So that's the form, and as soon as you see that form, you could be done and say, yeah, that's a valid form. It's transitive reasoning. And unless the question said specifically to do a truth table, then that's it. Done. Valid. I'm done. I would like to just take a little bit of extra time to go through the truth table for this one, because this one is just slightly different in the fact that it has 3 variables, and I just want to touch on how that looks in the truth table if you had to do a truth table with 3 variables. So there's the first premise, there's the and there's the second premise, Q implies R. Then, as we always will do, take each premise, link it together with an and, group them all together as a one single statement, all of which will then imply the conclusion, which is the P implies R. So that's my rewriting the whole entire 3 lines of the argument all as one single line, one single statement. And ultimately what you're really trying to do is look at all the situations where all of this, assuming that that's actually true, is there any way that this guy could actually be false? Because if that was the case, then the whole thing is false, and you could say invalid. But we'll discover that there is no way, depending on any possibility for P, Q, and R, there's no way for that to ever happen. You'll never have this true while this is false, and that's why this thing is valid, because that simply doesn't happen. You can't have both of these true and that false simultaneously. It just can't happen logically. By the definitions of the conditional and the and, it won't happen. So we wouldn't, it's not obvious. So that's why we do the truth table. So, and because this truth table has three variables, it creates 8 cases. And um, maybe I'll take a minute here. Let me just create a new page. When there are two variables, there's 4 rows, right? Because you're going to look at all the cases, both true, first true, then false, then true, then both false. If there's 3 variables, it doubles the number of rows. And that's because that one extra third variable could be true or false in each of the previous 4 cases. That's why it's going to keep doubling. There'd be 4 variables, would actually make 16 rows. Now let's see kind of how do you enumerate all those different possibilities. So if we have P and Q and R as the 3 variables, there are many different ways that you could go through, at least 2 very obvious ways that you could go through. There are, well, there's a little, there are whatever 8 factorial. 8 factorial, that's a really big number. There are actually 40,000 different ways, 40,320 different ways that you could list all of the cases. Um, Only 2 of them are very common, and you could use, well, really any of them, but most people will go one way or another, and I'll talk about those 2 very common ways of listing out all the cases. So the way that I like to explain it is that if you had only 2 variables, if there were only 2 variables, of course, there are 4 cases, and these are the 4 cases with 2 variables. And so my argument for why there are 8 rows is because in those 4 cases, your third variable could be either true or false. And so we want to list out both of those 2 possibilities. So I could go through all 4 cases with R true, and then just repeat those 4 cases with R false, and that gives me every case, every one of the 8 cases. So I need to go back again, true, 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 false. So now I have the 4 cases when you have 2 variables, and then I've repeated the 4 cases when you have 2 variables. And in the second 4 cases, the third variable could be false. So now I've gone through 8 different cases with my 3 variables. Now, it it doesn't really matter what order you put the 8 cases in if you're doing the truth table, because you just need to have all cases there. And so another common thing that people do when they want to list out all of the 8 cases is that, and it doesn't really matter. So they'll just say, let's do one of the variables, do repeat true 4 times, and then repeat false 4 times. And then one of the variables you repeat um, true twice, and then false twice, and then true twice, and then false twice, and then just alternate in the third variable, true, then false. So it would mean that we would be in a slightly different order because, we could get all the cases this way. They're just going to be in a different order, but they'll all be there. The other common thing to do is just to go 4 cases where P is true, and then 4 cases where it's false, because it could be just Q and R were my original 2, right? So this could be both true, and then both false. I mean, true, true, and then false, false, and then true, true, false, false. And then just in the last one, just alternate. So this works also either way. Um, I like to do it this way because it gives some justification as to why there are 8 cases. When you do it this way, you get all those 8 cases, but it's not totally clear why you have to do that. Um, and so, but either one. Okay, so that's what happened in this particular argument. It was there were 3 variables. We were looking at an argument. First premise P implies Q. Second premise Q implies R. conclusion P implies R, we have P, Q, and R, and I went through and did both true, true, false, false, true, false, false, and then I repeated again, true, 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 false, false, true, false, false. And in the third variable, I did 4 true and 4 false. We could have, you could change, that's all the 8 cases, but you could change which one you wanted to do 4 in a row, 2 in a row, etc. But in the end, going through the truth table for this premise and this premise all implies this conclusion. Whatever order you do all of these cases, the answer is going to come out all of these cases, the entire statement is true, meaning that the argument is a valid argument, always true. It basically means that there is no situation where this whole entire statement is true and this statement is false. That just never happens. That what you have here is true and simultaneously what you have there is false. That never happens. Because if it ever happened, one of these would have been false. It never happens. It is always true. So this will always imply that. This whole argument is always true. This is a valid form of reasoning. And so that's the answer. Because this is true in every case, the argument is a valid argument. Okay, let's look at my next example. Example 6. Example 6. If you study hard, then you will do well on the test. P implies Q. You do not, you did not do well on the test. So that's negation of Q. Therefore, you did not study hard. So the conclusion is negation of P. So again, I could do the truth table, but I recognize the form. This is a valid form. Specifically to the question here, all I have to do is say it's valid. I will usually ask as a test question, what's the name of this form? And the name of this form is, you could say contrapositive. It's got several names. Contrapositive reasoning. You could call it indirect reasoning. Or you can go with the Latin name, which is modus tollens. Any of those are correct names for that form, and it is a valid form. Okay, example 8. If you study hard, then you will do well on the test. This is another conditional. P implies Q. You do not study hard. That's negation of P. Conclusion, you didn't do well. That's negation Q. So that's invalid. The name is fallacy, the inverse. This one makes me think about sometime I'll do a video on the distinction between necessary and sufficient. But anyway, the topic here is just specifically on identifying valid versus invalid arguments using truth tables and recognizing their form, which comes from the truth table. And so that's the answer for example 7. We got one more on here, example 8. I will finish the video or do another example. I will not do another example, therefore I will finish the video. So this is an or, so we'll say P or Q. I will not do another example, so that is negation Q. So my conclusion is I will finish the video, P. So what about this form? P or Q, not Q and therefore P. Yeah, I don't really have to do the truth table. I recognize the form. It's a valid form. It's just valid disjunctive reasoning. I can sort of reason it out without doing the truth table, either by recognizing the form, or really what I just did there as I was looking at it, as I thought, I know the rule for or is it would be true if either or both is true. So we got in the first premise that either or both are true. Then I see negation Q. So if I know that it's not P, then I know P. If I know it's not Q, then I know P must be true. It's all sort of an intuition that I'm using there, rather than actually recognizing the form. I know P or Q, not Q, and therefore P. If one or the other or both is true, and it's not the one, it must be the other. is sort of my intuition as to where I can spot, oh yeah, that is a valid form. So answer is valid. The name is just valid disjunctive reasoning. Okay, so that really is the end of the video. I hope that was a helpful video. I guess there is just one last parting thought that I want to make, and that is that ultimately there are infinitely many different kinds of arguments that could be presented and analyzed with a truth table. And ultimately, if you didn't recognize the form, you use the truth table to determine the validity of the argument. I've presented four that are valid and four common forms that are invalid. And so we can save time and not do the truth table um, when you recognize whether it's one of the valid or invalid forms. And so you don't have to do the truth table in those cases. And again, I got to say that unless it's specifically said in the question to, write the symbolic form, maybe name the form of reasoning, and create the truth table for the argument to determine the validity, that could be a question on a homework or on a test. If it asks for the truth table, of course, then you do it. But if it's one of these 8 forms, either for valid or invalid, that you recognize, the point was you didn't have to do the truth table in those cases. All right, so there, I'll close with that.